Hi everyone, welcome to the fourth lesson for topic 4.5 Energy, Work and Power. So we are going to continue our previous learning outcome, which we talk about the relationship between the change in energy and also the work done by the external forces. So this idea is represented by the work energy principle that we learned, right? So for today's lesson, we are going to look at the part for principle of conservation of energy. So you will actually realize that a lot of things that we're going to do is still based on work energy principle, but it's just that maybe in an easier approach after you understand how conservation of energy works. So it's just like a further idea on work energy principle. Okay, so let's start with a recap. Okay, in the previous lesson, we know that work energy equation tell us that the total work done by all the forces, including the weight, will be equal to the change in the kinetic energy, right? Okay, so when we further explore this equation, then we realize that for the object that move in a vertical motion, so which means if let's say this object is under a free fall, so the distance from the ground to the initial position of this object is like given x maybe. Okay, so when we try to find out this object is under a free fall, right? So which means that there will be a work done by the gravity because the weight or the gravity is in the same direction with the motion. So it will be equal to F times the distance. So the F here, the force here is the weight, right? Which is given by mg. The distance here is x. So when we try to find out what's the change of the gravitational potential energy for this object, so let's try to denote here the ground is at 0, then the height here is x, right? So that's why when you try to use the final gravitational potential energy, which is 0, to minus off the gravitational potential energy at the initial position, which is given by mg and the h is x, then we realize that it gives us negative mgx. So by having this, then we know that the work done by the gravity is actually equal to negative the change in the gravitational potential energy. I hope that it makes sense to you so that you can understand it as if work done by gravity is like a positive number that is going to help you to speed up the motion, right? So when I talk about the GPE, it's like depending on the height. So you can see when this object is experiencing a free fall, so which means the height of this object actually decreases. So that's why there's a decreases in the gravitational potential energy. So when we try to equate them together, it's like the work done by the gravity is equal to negative of the change in gravitational potential energy. So after we get this idea, then we come up with the other form of work energy principle, which tell us that the total work done when we try to exclude the weight or exclude the gravity, then it will be just equal to the change in kinetic energy and then plus the change in gravitational potential energy, which imagine that is from this place negative GPE. So when you move to the back, so it become plus the change in GPE. Okay, so I hope that by this time you are pretty familiar with these two equations already. So for today's lesson, we are going to use a lot of this second equation to understand it, because when we talk about the conservation of energy, right, it's including of kinetic energy and gravitational potential energy and what's the relationship between them. Okay, so let's move on to the introduction part. Okay, so before we discuss about the conservation of energy, let's try to understand the difference between a conservative force and also a non-conservative force first. Okay, so there are these two types of forces of the system that we're going to look at later. Okay, so a conservative force is any force for which the work done by the force in moving a particle between 2 points is independent of the path taken. Okay, so the difference between them is that for conservative force, the work done is path independent. So which means it doesn't matter like is it the path is a zigzag one or the path is a curved one. So what matters is like the initial position and the final position. Then for non-conservative force is going to be depends on the path taken. Okay, so now you can try to imagine what type of force is actually conservative force. So for example, the first one is the gravity, okay, or we can measure it as weight, because when we talk about the force, right, it's actually depending on how high, what is the height of the object, right? So we know that the work done by the gravity is basically equal to the gravitational potential energy, and that's like the vertical distance. So I'm going to give like two more example, which is not so much, is like not involved in our syllabus, but it's also one type of conservative energy. So like the electric force and also the elastic force. Okay, so you can see that majority of the conservative force is related to the stored energy. So like the potential energy that's like inside an object. So whereas the other hand, we have non-conservative energy. So you can actually imagine that what is a type of force that actually path dependent. So I think the first one is very easy. So all the applied force are non-conservative force. So when you are trying to push something or you are trying to pull something, so how are you going to push it, or what is the path that you are pushing them is matter, correct? So are you pushing them in a curve shape or are you pushing it in a straight line? That actually makes a difference. So it's the same thing as well when we talk about like driving force also. Okay, so are you going to drive the car in a zigzag direction or in a straight line direction? So as we have the applied force and the driving force, then we know that the force that opposing the motion is going to be non-conservative as well, right? Because it's depending on your path also. So we have friction as well. Okay, and the last one is the one that we didn't talk about it a lot, but air resistance is one of it. Okay, so that's why you can imagine if like for a heavier object that's trying to like under a free fall that straight away fall down, then you compare to like a feather maybe, then it's going to be like going zigzag, then you can realize that the air resistance for this is going to be like larger than this one because of like the path that it takes. Okay, so yeah, I'm just using like these ideas to let you understand, so you can see that both of these particle is actually at the same height. So we are talking about the initial position, then the final position. So which means if let's say this particle is going downwards in a straight line position, right? Then we know that the friction, the applied force is actually based on the path here. Okay, but when we talk about the gravity and the weight is basically between the height. So it's the height that matters. So that's why you can see that no matter how the path is, as long as the height is the same, then the work done by the gravity will actually be the same. Okay, but for applied force, for driving force and friction, if let's say you are going through the path of like a zigzag or a curvy one like this one, then you realize that the force that you have is going to be like larger than this one. Because sorry, let me try to rephrase my word, the work done here is going to be like much more larger than this one because you have a higher distance when you try to compare to a straight line motion. Okay, so yeah, this is like just an explanation. So the work or the weight and the gravity, yes, is an example of conservative force because the work done by the gravity depends on the change in the, yeah, the position only, right? So that's why we only mention about the vertical distance. Okay, so you can see as long as the vertical distance is the same, which means the work done is going to be the same. It actually did not, I mean, it doesn't depends on the path or the shape of the path that this particle taken. But whereas the other way, the friction and driving force are not conservative force because the work done depends on the length of the particular path travel. Okay, so if let's say the path is like a longer one, that's going to be like, if let's say it's a zigzag one, although it's reaching the same position then, but then it's going to give you a larger work done because of its distance traveled. Okay, so yeah, that's the idea of it. So now we'll be looking at what how does that look like when we try to look at a system with only conservative force and the system with non-conservative force. Okay, so let's start with an easier idea which you only have conservative force. Okay, so in our syllabus, right, the only conservative force that we encounter is the weight only. So you can imagine that in this case, that which means I have the weight here. Okay, then I have my normal reaction, which is not going to be much related when we try to calculate the energy, right? Because when we calculate the work done, so this is the force that is perpendicular to the direction of the motion, so which is not going to be taken into our consideration. Okay, so this is the only forces that we have. So this object is basically slipping down lah. So you can understand like the weight, right? So this is the only force that acted on this object. Okay, so since we learned that the total work done will be equal to the change in kinetic energy plus the change in the potential energy. So you would realize here that what's the total work done in this situation? Because when we are using this equation, we are not, I mean, the work done is excluding the weight. Am I right? So that's why the total work done in this case will be 0 because there's no other work done other than the weight here. So that's why the total work done here is 0 and it will be equal to the change in KE plus the change in GPE. So when we try to rearrange this equation, and it actually gives us that the change in kinetic energy is equal to negative the change of GPE. Okay, in other words, when we try to take into the consideration of the sign here, so you can see that this is a positive change. So the gain in the kinetic energy will be equal to the negative change, so which means it's the loss. So the gain in kinetic energy is equal to the loss in the gravitational potential energy. In other words, you can also say that the gain in the gravitational potential energy will be equal to the loss in the kinetic energy. Okay, so when we try to further expand this idea, then what you can see is that the change in kinetic energy, so which means it's going to be the kinetic energy. I think it's okay for me to write here. So the kinetic energy for the final minus of the kinetic energy initial, right? So that I can get the change in kinetic energy will be equal to negative PE GPE final minus of GPE initial. So when we try to rearrange this equation and I mean you try to like expand this, and what do you realize here is that you realize that KE final plus GPE final is going to be equal to your KE initial plus GPE initial. I hope that you can see that. So this is negative, right? So when you move to the front, then it become plus. So this is negative. When you move to the back, then it become plus. Then negative, negative, which give you a plus here. Okay. So from what we can see here, which means that it tells us that the kinetic energy in the final stage plus the gravitational potential energy in the final stage is going to be equal to the kinetic energy in the initial stage plus the gravitational potential energy in the initial stage. If let's say when we try to understand it in a form where we know that mechanical energy actually consisted of both kinetic energy and gravitational potential energy, right? So that's why, which mean in another words, the total mechanical energy didn't change from the beginning until the end. So you see the total mechanical energy in a final stage is going to be equal to the total of the mechanical energy in the initial stage. So this idea is actually called as the conservation of mechanical energy. So which means it's not only about the initial and the final, it's like for any point of your position, if let's say the system only consisted of conservative force, then all your mechanical energy will be the same throughout the whole movement. So for a closed system of conservative forces, the total mechanical energy, kinetic energy plus gravitational potential energy is constant. Okay, so the idea is that at any point they should be the same when you try to plus them together. So this idea we call it as the conservation of mechanical energy. Okay, so let's try to understand it further. So when the work is done by a conservative force, it changes the store potential energy. So in our case here, our potential energy is mainly on the gravitational potential energy lah. So it changes the store potential energy into kinetic energy. So you realize that the energy that interchange here is just like potential to energy. So in the previous notes, we talk about the loss in potential energy is going to be gained by the kinetic energy. Am I right? So both potential and kinetic is actually mechanical energy. So that's why there's no loss in mechanical energy. Okay. And something that's special about the system with only conservative energy is that all this energy can be recovered again to be the potential energy by reversing the effect. Okay, so let me try to explain this by using this simple diagram. So imagine this is like a movement of a particle. So this thing is like going down, then after that going up again. So this position is basically the same, so which means they are in the same height. Okay, so now let's try to understand it like this. So when this object is started at rest, right? So which means at this point, if it's at rest, then which means the kinetic energy here is going to be zero. Okay, then let's try to imagine that maybe in this case the GPE, okay, maybe the mass is like 1, then times 10, then the height here is 5. Then we try to assume that the GPE here is 50. Okay, so you can imagine, right, when this thing start to move, then the height is reducing. So we can expect that the GPE is going to be reduced. So that's why in this case, maybe the GPE is going to be only 20 here. So you can see the GPE actually decreases for 30. Okay, for 30 joules. And then where is this 30 joule go? So you realize that this thing starts to move, right? So it has a certain velocity here. So actually this loss of 30 joules of GPE is going to be in the gain of the kinetic energy. So it's going to be 30 here. So you can see that when you look at the stage, right, the sum of the kinetic energy and the gravitation energy is 50. So at this point, it's going to be 50 as well. So now, which means if let's say this object is at the lowest point, then which means this is the part where the kinetic energy is the highest. Am I right? Because that should be the place that it has the maximum velocity. So in this case, the GPE will actually become 0 because it's at the lowest ground here. So that's why this 50 of mechanical energy actually all goes into the kinetic energy. So now you imagine that these objects continue to move, okay? And you must remember this idea we talk about, there's no other external force other than the gravity here. So that's why there's no friction, there's no other form of energy that this mechanical energy is going to be lost to. So that's why in this case, when it go back to the initial height, then it's the same place. This is the maximum height, right? So the KE will actually goes back to 0 because at maximum height, the velocity is 0. So when it go back to the same initial height, then which means the GPE will go back to 50. Okay, so I hope that by using this simple idea, you can get the idea where what is that meant by the gain of KE is equal to the loss in GPE, and what is that meant by the total mechanical energy at every stage. It should be the same if let's say we have a closed system of only conservative energy. Okay, so this is like the idea. So you can see the total energy in all the stages is all 50. So whatever that is lost by KE is going to be gained by GPE. Whatever that's lost in GPE is going to be gained by KE. Okay, so that's pretty much the idea. Okay, so now we'll be looking at two simple examples. Then we'll move on to the second part, which we'll try to look at the system for which you have a non-conservative energy. Correct. Example 1, a box of mass mkg is initially at rest, so it slides down a smooth slope that is inclined at 30 degrees to the horizontal. So question 1 is to find out the speed of the box after sliding a distance of 3 meters. Okay, so which means this is like 3 meters sliding down. So this is the box, okay, of mass of mkg. So this is mg. So I know that we have the normal reaction, then this is going to be 30 degree. Okay, so that's basically the idea, and the question didn't mention the other force. So you can see that this is a system that only consisted of the conservative force only. Okay, so which means in this case, you can try to deduce either the change in KE equal to the change in negative change in GPE, or you can try to do the total mechanical energy in any stage, it will be the same. Okay, so depending on you, so I'm trying to do both so you can understand for the first time. Okay, so let's start with, if let's say we try to use the change in kinetic energy will be equal to the negative change in the gravitational potential energy. Okay, gain in KE equals to the loss in GPE. So in this case, maybe since we need to find GPE, which means we need to find the height. So you can just roughly draw a simple triangle here. So this is 30. Okay, then this is our h, right? So this is 3 cm. So that's why, sorry, 3 meter. So that's why it's going to be like our h is equal to 3 sine 30. Okay, so I hope that you should be pretty familiar with this idea already. So now let's try to move on. Okay, so what's the change in the kinetic energy? It's actually started from rest, right? Then we are going to find what's the speed here. So the final is the V that we want to find. So half the mass in this question is M. Okay, then after that V square is what we want to find. So it's initially at rest. So that's why 0 square. Okay, then equal to negative. So now you try to find out the change in GPE. So the change in GPE here, mgh. So the m here is m, the g is 10. Okay, so what's the initial height here? So the initial height here is h, right? So which means it's like 3 sine 30. Oops, I'm sorry, should be final minus initial, right? My mistake. Okay, final is at the ground, so that's 0, minus of the initial height, which is 3 sine 30. Okay, so now let's try to expand it. Then we have half mv squared will be equal to 10. So sine 30 is going to give us half. So 1.5 times 10, so it's 15. So that is 15m. Okay, so yeah, you can try to solve this out. So like 10m, negative 10m times negative, so you get a positive answer, right? So 10 times 1.5 is 15. Okay, so now let's move on. So you have m and m, so that's why you can just eliminate them. So we have half v squared equal to 15, and that gives us v squared equal to 30. So v is the speed, so we only take the positive side, so which is 5.48 meter per second. Okay, so this is by using the first approach. So the second one is, if let's say you try to use the idea of mechanical energy is the same throughout the process, it's going to be the same. So which means that you can try to do the kinetic energy initial plus the GPE initial, okay, and then equal to the KE final plus the GPE final. Okay, so in this case, the kinetic energy initial, since the V is 0, so that's why it's 0, right? So the initial gravitational potential energy is the mass times G, and then times the height, which is 3 sine 30. Okay, then the final kinetic energy is half, then m v square is what we want to find. So the GPE for final is on the ground, so that's why it's 0. So when you try to solve it, then you realize here that this you get 1.5 again, so it's 15m, then equal to half mv square as well. So you realize that you get the exactly same equation. Okay, so I'm not going to continue that. So just to show you that the idea is the same. Okay, So yeah, this is like extra notes for you. You will realize that when you try to use the normal work energy principle to solve this, meaning like the total work done equals to the change in KE, you are going to get the exactly same answer as well. Okay, so as what I mentioned at the beginning of the lesson, right? The idea is that what you are doing is still the basic, is still on work energy equation. So when you try to use work energy equation to solve everything here, you can actually solve it. But the idea is maybe you can try to use an easier approach if you understand the idea of the conservative energy. Okay, so that's pretty much the idea. So that's why if you feel confused that how come I cannot use like the total work done equals to the change in kinetic energy? Yes, you can do that and you will get the exact same answer. Okay, so now example 2. Okay, number 2. So this is another simple idea. So there's a ball of 0.05 kg is thrown vertically upwards from a height of 1.5 meter from the ground. Okay, so maybe it's something like this. So this is 1.5 meter. Okay, then after that, the ball rises through a height of 2 meters. So the ball is now here. So this is 2 meter to reach its maximum height from at 3.5 meter above the ground, right? So use the conservation of mechanical energy to find the initial speed of the ball. Okay, so yeah, depending on you. So when we talk about the conservation of the mechanical energy, you can either do the loss in Ke equal to the gain in Pe, or you can try to do the at any stage the mechanical energy is the same. Okay, so yeah, let's try to do that. So the change in Ke equal to negative change in GPE. Okay, so in this case, we want to find the initial speed, right? So which means this is the u that we want to find. So when it's at the maximum height, the velocity should be 0 here at the final stage. So the change in kinetic energy is half. So the m here is 0.05. Okay, and then v square 0 square minus of u square equal to the change in GPE. So in this case, we have m 0.05, g 10. Okay, you might want to do like this. Yeah, then the final, this will be an increase, right? So that's why if we try to treat this as 0, then our final here is going to be 2. The height here is 2. Then minus of the initial, which is 0. Okay, so let's try to continue to solve that. Oh yeah, when you try to use this formula, right, make sure that, okay, if you were to ask me whether to use this or you use the initial plus initial then final plus final, which one is going to be much more safer, then I'll say use the second one is safer. Okay, the idea is that when you try to talk about the change, right, there'll be a lot of things that you need to be a little bit more careful when you deal with the negative sign lah. Because sometimes when you try to solve like this, then you will tend to like ignore the negative sign here. Then when you try to do the final position or the initial position, then whether you want to write the positive height or negative height, then you will tend to be a little bit confused there. So that's why by using the second form of equation is actually safer in that sense. Although maybe you need to write a little bit longer. Okay, later we'll try to do that again, then you'll see a difference. So that's why you see this is 0 minus u square. So make sure that you have a negative. So 0.25 u square equal to, so the same thing here, negative, this is positive 2. So that's why you have a negative answer here. So that gives us 0.5, so 1. Okay, so u square is equal to 1 over 0.025, and that's 40. So u is equal to, same thing, u is a positive answer. So u is 6.32 meter per second. Okay, so now you see, right, when we try to compare to the second one, then you have a lesser risk of whether you write it like mistakenly writing it as positive or negative, because what are we dealing with is just like plussing them together, right? So Ke final plus GPE final, and then equal to the Ke initial, then plus the GPE initial. So you doesn't really need to deal with like positive and negative, but you just substitute, am I right? So final then, which means that you have half m, so final is 0, right? Yeah, and then plus the GPE for final, so it's at the highest point, which the height is 2, so that's why 0.05 times 10 then times 2. So KE for initial is what we want to find, so 0.05 and then U square. Okay, then plus the initial, then we know that at this place is where we try to note our height as 0, right? So that's why it's 0, or if you want to write then 10 then 0. Okay, so you realize that I mean, it is not that confusing when you try to compare to this in terms of the sign of your equation. That's basically the difference. Other than that, then I think it's basically the same. So you see, you can straight away like getting a positive answer. Then after you solve that, it's just going to give you the same thing. Okay, so that's pretty much the idea. So again, I want to note that if you are using work energy principle, you can do that as well. But then it will be an easier case when you try to solve it like this. Okay, so now we'll move on to the second part of the notes, which we talk about if let's say the system have a non-conservative force. Okay, so for the system having non-conservative forces, we are going to look at it by two different situations. So the first one is, if let's say we have a force that's, okay, so same thing, we try to denote that this particle is going to slip down as well. Okay, but in this idea, we have maybe is a push, or in this case, maybe, okay, it's like a driving force. Okay, so you are like driving, so that's like a driving force that in the direction of your motion. That same thing, we have the weight here and also the normal reaction that's not so related. Okay, so if let's say the first case we are looking at, this is the work done by a conservative force, right? Because it's in the direction of motion. What happened here is that it converts the energy into movement, okay, or into like motion or anything like that. Okay, such that in this place, if let's say we are talking about the driving force, right, then it's actually converting the chemical energy from the field to kinetic energy. So if you are saying that it's a push, then which means you are trying to converting an applied force to an kinetic energy so that this object can move like faster, can speed up, right? So that's why when we try to do this, then what can you realize here is that the same thing, total work done, it will be equal to the change in the kinetic energy plus the change in the gravitational potential energy. Okay, so in this case, our total work done excluding the weight because we are using KE plus GPE. So that's why the total work done here is only the work done by the driving force. Am I right? So that's why it's the work done by. Then it will be equal to the change in kinetic energy plus the change in gravitational potential energy. So we know that the work done by the force is going to give us a positive answer. Am I right? So that's why the change in kinetic energy and the change in gravitational potential energy is going to be like positive. So that's why the work done by is like equal to a positive change in mechanical energy. So you see the total energy is conserved, but the mechanical energy is actually increases. I hope that you get what I mean, because when we try to talk about the total energy, which means it's like the energy from the chemical energy, the weight here, and then also with like the force, I mean the, if let's say you have potential energy in this case, right? So which means we talk about the potential energy and the chemical energy. So in this case, the chemical energy is lost, right? But then the chemical energy actually goes into the kinetic energy. So that's why our total mechanical energy increases. But if let's say we talk about the total energy, then it's still the same because you can't create like extra energy from this system. You get what I mean? But it's just that it transforms from the form of chemical to become mechanical energy. So that's why the total energy is conserved, but mechanical energy actually increases. Okay, so now let's look at the other case. If let's say there's a work done against a non-conservative force, so which means the same thing, this object is slipping down, so we have the weight, then we have the normal reaction, but then in this case we have maybe the friction opposing the direction here. Okay, so what happened here is that it's the opposite idea with what we mentioned just now. So if this is the idea, then which means that it actually converts the movement into other form of energy. So for example, you see, right, when we talk about friction, because by using a simple idea, then you should know that, I mean, you can't create energy from something that's like nothing, or you can't actually, the energy wouldn't be like lost, then after that, you do not know where it goes. So the idea of friction is that when friction involved, then which means, I'm sorry, I supposed to write heat energy, okay? So when friction happens, so you can see that it actually opposing the motion. So it actually makes the particle to slow down. In another words, which means the kinetic energy of the object actually decreases. So if the Ke decreases, then where the Ke goes to? So in this case, if let's say there is a friction, which means that the kinetic energy here actually transfer to be the heat energy. So that's why the mechanical energy is lost. Okay, so this energy is lost from the mechanical system. So which means that it goes from back from movement to other form of energy. So it's like opposite way with the first one. So the same thing we can try to understand it from the work principle energy as well. So the total work done is equal to the change in Ke plus the change in GPE. So when we talk about the work done against, right, so normally we'll use minus, am I right? So when we try to find the total work done, we use the work done by minus the work done against, then equal to the change in Ke plus the change in GPE. So you'll realize that when we try to equate them, move the negative to the other side, then you can get that the work done against is equal to negative of the change of Ke plus GPE. So in this word, then you can see that the total energy is conserved, meaning that heat energy is considered as energy. So the total energy doesn't change. But then because of some of your kinetic energy, or maybe in this case, that is like the loss in potential energy as well, right? So it transformed to other form of energy. So that's why the mechanical energy is actually lost, or some of the mechanical energy decrease. Okay, so it's lost. So that's the idea of it. Okay, so I mean, you can understand it by using a very logic idea. So this is like the work done by something that's helping the motion, right? It's speed up the motion. So that's why it's going to be a positive idea. Then this is again, so it's opposing the motion. So obviously there will be a loss in your total energy. Okay, so unlike the situation when there is only conservative force, so for non-conservative force, the original situation cannot be recovered. So you remember the shape that I draw just now. So we say that at every point, the GE and the KE, when you plus them together, is the same, right? But in this case, if let's say you have a non-conservative force, it cannot be recovered. Okay, so because some of the energy can be, change to non-mechanical energy, or like the non-mechanical energy already changed to mechanical energy. So you imagine if let's say you already changed the field which from chemical energy to mechanical energy, you wouldn't be able to like, you slow down, then the field will increase. That doesn't, it is not logic, right? So it's the same thing then when the motion is already, the kinetic energy already transformed to heat energy, you cannot say that I want to reduce the heat energy, then maybe the kinetic energy can be increased. So that doesn't looks logical as well. Okay, so the idea is it cannot be recovered. So it's not the same thing like just now. Okay, so yeah, the same thing for this case also. So something that's helpful is by using this one, maybe you can solve a little bit faster. But the idea is that when you try to use the work energy principle, it's still going to give you the same answer. So later I'm going to like do everything in one partial question, then you'll understand like actually all formula works. It's just that which one you want to use only. Okay, so now let's try to look at example 3. Okay, a ball of mass 50 gram falls from rest through a height of 80 cm. It hits the ground and rebounds to a height of 30 cm. Okay, so maybe let's try to draw it. So that's this ball. So the height. 80 cm, so that's 0.8, then hit the ground, then rebounds at a height of 0.3. Okay, so when you try to look at this situation, I hope that you can straight away get that this is the idea where you have a system that is consisted of non-conservative force. Okay, because if let's say you have only conservative force, the KE and the GPE at any point should be the same. So which means that there's no loss of mechanical energy. Then this ball should fall from the same height. Then after it rebounds, it should go back to the same height so that you have KE and GPE is the same. So by looking at this idea, then you should realize here is that there are some mechanical energy lost throughout the way so that when it rebounds, then the ball cannot go back to the same height. Okay, so that's the idea. So the question wants us to find out the mechanical energy loss in the motion from the start at a height of 80 cm to the end at the height of 30 cm above the ground. So what's the mechanical energy loss? Okay, so this is not so much about the formula yet. I guess it's just a very simple one for you to understand the idea of mechanical energy loss. Okay, so let's try to solve this. So maybe we can try to find out one by one maybe. So the change in kinetic energy first. So you'll realize that at this point, if let's say it's force from rest, so at here U is 0. So this is the rebounds to a height of 30 cm, right? So this is like the final height, which is like the maximum as well. So that's why you can imagine when you try to find the initial kinetic energy and the final kinetic energy is still going to give you 0. So the change in kinetic energy is actually 0. So let's try to find out the change in GPE then. Okay, so the final, so which is at this point, so let's try to denote this as 0 meter. So mgh, so 0.05 times 10. So the final height is at 30 cm, so that's 0.3 meter. Okay, then minus of 0.05, I should factorize it. It's okay lah. 10, and then after that, the initial is actually at 0.8. Okay, so let's try to solve this. So we have 0 point times 10, 0.5, so 0.15. Then minus of 0.5 times 0.8, so that's 0.8. Sorry for that. 0.05 times 10 times 0.8. So yeah, that's 0.4. Okay, then when we continue, oh yeah, that's right. I was like confusing with my, okay, so negative 0.25 joule. Okay, so that's why you get a negative answer. So you know that it's a loss lah. So the mechanical loss is basically the loss for both KE plus GPE, and that gives us negative 0.25 joule. So that's why it's a loss. So loss in ME is equal to 0.25 joule. Okay, just like that. Okay, now example 4. Okay, number 4, a parcel of mass 3 kg slides 3.5 meter down a rough slope inclined at 20 degree to the horizontal. So let's try to draw it out. Okay, so we have 20 degree. So this is the parcel, mass of 3 kg, so that's 30. Okay, so slide down for 3.5. So the coefficient of friction, so that's friction. So it's 0.5 for the coefficient of friction, then normal reaction. So this is 20. Okay, so when it reaches the bottom of the slope, the parcel has a speed of 8 meter per second. So which means the V is 8 lah. So the question wants us to find the speed of the parcel at the top of the slope, which is U. Okay, so for this question, then you have a friction. So that's why you have a non-conservative force here. And if you can recall, then the work done against, right, because this is the friction. So the work done against will be just equal to negative the change in PE plus the, sorry, let me try right, not confuse you. Yeah, the change in KE and then plus the change in GPE. Okay, so in this case, because you realize here that there's only like one force that goes against. So if not, then you might want to just use a normal work energy principle. And actually, when I try to look at this, right, then you'll realize here that when we talk about work energy principle, it's just the work done by minus of the work done against, then equal to the change for KE plus GPE. So you realize that when I move the negative sign to the front, right, it's just basically the work energy principle. So if you were to ask me, right, I will feel that for the situation where you have a non-conservative force, actually the shortcut of the equation actually doesn't matter that much. It's not as useful because at the end you are just doing work energy principle lah. So no need to just remember like one more time the formula that like work done by equals to the change in KE plus the change in GPE. Until the end you are still doing the same thing. So for the part where you have all the conservative force, then the part where the change in KE equal to the negative the change in GPE, that one is helpful. But for this one, it's actually just the same thing. I mean, it doesn't matter whether you use the conservative or not. Okay, because at the end the energy is not conserved, right? That's like increase or decrease happen. Okay, so yeah, let's try to just solve this quickly. So we have the work done against, so which the force here, because when you try to use this equation, which means the weight is not included. Okay, so we have the force here, then it will be the friction. So mu r. So in this case, we have our mu is 0.5. So R in this case, then I hope that by now you can straight away look at it. So 30 cos 20. Okay, and the distance traveled is like 3.5. So since you are using against R, so that's why there's no negative here because you already changed the negative to the back. So minus of the change in kinetic energy. So we have half mv square, so 3 kg. The change, so the final is 8, okay, minus of u square. Okay, then after that minus another GPE, so we have what 310. Okay, how about the height? So same thing, this thing, right? So we have 20 here. So we want to get the height, and then this is 3.5. So that's why it's going to be sine as well. Okay, so h equals to 3.5 sine 20. So that's our final. So the final is 0 minus of the initial height, which is 3.5 sine 30 sine 20. Okay, so just put inside. Yeah. Okay, so now we can try to solve it. So multiply the number together and I can get 52.5 cos 20 equal to negative 364, so 96 plus 1.5 u square plus 105 sine 20. Okay, let me repeat it again. So make sure you are aware of the positive sign, negative sign. Especially like this part, it should be a plus. Then after that, when you do here, then it should be negative, then positive. Okay, so when we solve it, then we can get 1.5 u square equal to 109.4217, and solving this, and it gives us 8.54 in GSF. Okay, so I guess this should be very simple because it's just work energy principle. So it's just that you memorize one more formula here, but if you are just using work energy, then it's going to work as good as this as well. Okay, so now let's try to look at last example, which we will be dealing with like two particle, and I just want to show you that no matter which idea that you are using is just basically the same thing. Okay, so let's look at the last one. Okay, so two particles A and B of masses 0.8 kg and 1.6 kg respectively are connected by this light inextensible string. Okay, so let us try to denote first. So that's the weight here, that's the weight here. Okay, then particle A is placed on a smooth plane, so that's why there's no friction. So where given the angle is sine theta equals to 3/5, so the string passes over a small smooth pulley P, then B hangs freely. So the particles are released from rest, so which means both of them is just having a UB here is going to be like 0, then the UA here is 0 as well. Okay, so after that, the question said that use an energy method. So that's why, by looking at this question, you can actually use Newton's second law of motion. But in this case, the question say use energy method. Okay, to find the speed of the particle after each particle has moved a distance of 0.5 meter. So assuming that A has not yet reached the pulley. So that's why by using your prior knowledge, then you should know that this pulley should move here, okay? And then they should be moving in the same acceleration. So that's why their V is going to be the same thing as well. So we can just try to denote like both, no matter it's A or B, is going to be like V because they are connected by this string, right? Then the distance of 0.5, okay? So yeah, that's the idea. So in this case, I'm going to show you different idea. Then at the end, I'm just going to prove you that actually no matter you are using conservative or you are using a normal work energy, it's just the same thing. It's whether it's either like which approach that you try to think of, then which one you are more familiar and which one you prefer only. Okay, so in this case, let's try to use the one that we just learned maybe. So in this case, you'll realize that there's no other force, right? The only force, because when we talk about the tension is going to be balanced off as well. So when we try to talk about the energy method, right, then is the idea where we try to combine everything together. So that's why the only force, the only work done by is actually only the weight here. So that's why this is a system of conservative force. So the first approach that we can try to use is just by using the change in KE will be equal to negative the change in GPE. Okay, so now let's try to do this. Or in this case, then I'll just write down lah. It's the same thing also if you want to use KE final plus GPE final and then equal to KE initial plus GPE initial. Okay, so personally, I prefer this because you don't need to deal with the very confusing sign. Okay, so yeah, let's try to find out maybe the height first in this case. So we have theta. Okay. Oh yeah, why do we need? So please remember when you talk about the distance of this thing, right? The 0.5 is basically like if let's say this particle is dropped here, then which means from here to here is 0.5. That's nothing wrong. But when you talk about this one, is the slanted distance is going to be your 0.5. So let me try to so which means if now your particle is here, so which means your 0.5 is here, it doesn't mean that your height is 0.5. It actually means that your slanted distance here is 0.5. So we need to get what's the height change here. So that's why h then 0.5. So the same thing, the h is going to be equal to 0.5 sine theta. Okay, so now we can continue the change in the KE first. So yeah, you need to take into consideration for both, yeah. So in this case, you have half. Okay, so depending on you whether you want to combine them together because at the end your V is the same. So if you doesn't want to, then it's the same thing as well. So half. So let's try to do for particle A first. So half m then V square. Okay, then after that plus, then you do the other side for particle. Oh, sorry, the change in KE, so it's minus 0, right? Because the initial is actually 0. So, okay, this is for particle A. So not confusing ourselves. Then now look at particle B. Then we have half, then 1.6. So V square also. Okay, and it's minus 0 as well. So equal to negative. So now let's try to solve solve for the GPE part. So for this particle A is going to be like a gain, am I right? So because this thing is like going up, so it's going to be 0.8, okay, and then times 10. Then after that, the height here is 0.5, so sine theta is 3/5. All right, and then minus of the other GPE. So in this case, it actually falling down. So we have 1.6, then times 10, Okay, in this case, the height is like from the initial is like dropping down, right? So the change it will be 0 minus of 0.5. Okay, final minus the initial. So initial is at 0.5, so 0 minus 0.5. Or you just put 0 negative 0.5 if you can understand. So in this case, if you want to write it in complete, then it will be 0.5 multiply 3 over 5. This one is minus 0 lah. Okay, because you get to a place that's like the initial here is 0, so final minus initial. Okay, so now let's try to solve this. So we have 0.8, so 0.4 v square plus 0.8 v square is going to give us negative. So in this case, 0.8 times 10 times 0.3. So that's going to be 2.4. Okay, and then minus of this side, negative, negative, that gives us positive 1.8, 1.6 times 10, 16 times 0.5, that's 8. Okay, so from here then we can get 1.2 v square equal to 5.6 and v square equal to 4.667. Okay, then from here then we can get our v greater than 0, so v is 2.16 meter per second. So this is how we solve it. Okay, so the idea is just the same where you try to look at like two particles, then you try to plus them together for the change, and for the change in KE, then for the change in GPE. Okay, so in this case, right, in other words, if you are using work energy principle, then which mean that the total work done is equal to the change of GPE plus the change in KE, right? So you realize that in this case, there's no total W as well. So that's why what you are doing here is just going to be 0. Then you get this. Then it's going to be exactly the same thing like how we start this question. So this is like another first approach. Then the other case, if you were to do it by using the first form of work energy principle, which you don't take out the if you don't take out the weight, then how is that going to look like? It's just the total weight, total work done, okay, equal to the change in KE, right? Okay, so in this case, the total work done is the weight that you have here. So that's why it's going to be this. Okay, let me try to draw. This is R. So this is your theta, right? So you need to make sure that it's parallel. So when you try to resolve it, then this will be your W sine theta, correct? Then after that, you have this side as well, which is going to be 16. So if you try to look at that, then it will be actually negative because it's against, right? Let me try to look at it again. So this thing is trying to move like this. So which means this force is actually against your motion. So that's why it's negative. Then 8 is 0.8 times 10 lah, your weight. And then after that, sine theta. Okay, and then times with the distance, which is 0.5. It's still 0.5 because you are looking at the slanted now. So then the other hand, then you have the weight here. This is work done by, because it's following the motion of your particle. So plus 16, which is the weight, and then multiplied by the distance traveled, then equal to half. Okay, so in this case, the change, then you will try to just combine them together lah, since you already know that it's the same. Okay, then when you try to solve it, then you can get negative, this is 3 over 5. So 2.4 plus 8 equal to 1.2 v squared. Then until the end, you realize that you're just going to get the exactly same thing as well when you try to compare to this. Okay, so you see the idea is roughly the same. It's just that whether which approach you like to do, either you prefer you solve it in terms of like the vertical distance, which you use GPE, which is like the first two approach here, or in another words, if you would like to, do not separate your GPE from your work done, then you are just going to resolve your weight to the direction of your motion, then you're just going to get the exactly same thing also. Okay, so it's just on your own preference. Okay, so that's the idea for this lesson, and we are going to cover the last part for the power in the last lesson. So yeah, feel free to, if you have any questions, so please let me know personally. Then spend some time to do your homework and also your revision for your test. So that's pretty much for today's lesson. Thank you.